Hello and welcome to this undergraduate skills video where we're going to learn about spectrophotometry, which will be extremely useful as you progress through your degree. Now, why do you need to know about this? Well, it will allow you to perform certain experiments and, more importantly, utilize the various laws that govern spectrophotometry so that you can calculate the concentration of unknown solutions using known samples. Now, this video is a little longer than some of the others in this series as there is slightly more theory to cover. So without further ado, let's get into the video and start with what exactly is spectrophotometry. Well, in plain and simple terms, it is a research technique that uses specialized equipment to shine light at a solution, measure how much of that light has been absorbed by the solution, and then calculate the concentration of solutes within that solution. And it can do this because of two very prominent scientific laws. We have Beer's law and we have Lambert's law. Now, Beer's law states the ability of a solution to absorb light is proportional to the solute concentration, which is essentially the amount of solute dissolved within a solution. Therefore, a solution with a high solute concentration is going to absorb more light than a solution containing a low solute concentration, which will absorb less light. And this is because the number of light absorbing particles within a solution changes. And so to see this visually, here we have a light source shining through two different solutions. One has a high solute concentration and therefore it appears much darker in appearance compared to the solution that has a low solute concentration. Now, as our light passes through the high solute concentration solution, more of the light is absorbed by the solute, meaning less light passes through the solution, resulting in less light being detected on the other side. Now, on the other hand, our solution that has a low solute concentration will appear much lighter in appearance compared to the solution that has a high solute concentration. And because there is less solute in the solution, more of the light can pass through the solution as there is less solute to absorb the light, resulting in more light being detected on the other side. Now, there are some potential problems with Beer's law, and this is where Lambert's law comes in. You see, Lambert's law looks at how far light has to travel through a solution, and this is because the further light travels through a solution, the more light will be absorbed by solutes in that solution. Therefore, if light travels a greater distance through a solution, it will interact with more solutes in the solution, and therefore more light will be absorbed. Whilst on the flip side, if light travels a shorter distance through the solution, then it will interact with fewer solutes in the solution and therefore less light will be absorbed. And so to see this visually, here we have a light source shining through two different solutions. One solution is in a wide beaker and therefore as light passes through the solution in the beaker, it interacts with more solutes before reaching the other side, meaning less light passes through the solution, resulting in less light being detected on the other side. Now, on the other hand, in our botany example, our solution is in a narrow beaker, and therefore, as light passes through the solution in the beaker, it interacts with fewer solutes before reaching the other side, meaning more light passes through the solution, resulting in more light being detected on the other side. Now, when it comes to practical spectrophotometry and Lambert's law in particular, the distance the light travels can be standardized in a relatively simple and efficient way by placing the solution we want to test in specialized square tubes which have a set length, the most common being 1 centimeter. Now together, as I said earlier, these two laws can allow us to calculate solute concentration in solution, and therefore we commonly apply both laws together, and in doing so they become the Beer-Lambert law. And essentially the Beer-Lambert law states the absorption of light by a solution is dependent on the solute concentration, the molar absorption coefficient, and the path length the light travels through the solution. So let's have a look at how we actually calculate the absorbance of a solution using the following equation. So the absorbance of a solution is equal to epsilon multiplied by C multiplied by L, whereby A is the absorbance at a set wavelength of light, which is unitless and given arbitrary units. Epsilon is the molar absorption coefficient of that solution, expressed with the units litre per mole per centimetre. C is the solute concentration, expressed as litres per mole, or as it is more commonly known, molarity. And finally, L is the path length through which the light travels, and this is given the units in centimetres. Now at this point, if you're not clued up on moles and molarity, it might be worth watching the associated videos, as this will help with some of the examples we see later on in this video. Now to break some of this down, we're first going to look at absorbance, which is the term used to describe the amount of light that is absorbed by something, and the amount of light being absorbed will change depending on the wavelength of light being used. So as an example, here we have an absorption spectrum for compound A, which is created by shining light of different wavelengths at compound A and seeing which wavelengths are absorbed and which are not. Now where we have a peak in our absorption graph, this indicates that this wavelength of light is being absorbed by our compound and doesn't reach our detector. Where we have this trough in the data, this would indicate that this wavelength of light is not being absorbed by our compound, and therefore it passes through our compound and into the detector. And so with an absorption spectrum like this, where red, orange, yellow and blue light is absorbed and green is not, compound A will appear green in colour. Okay, so going back, this absorbance value directly relates to the molar absorption coefficient, solute concentration and path length. Now solute concentration we've covered with Beer's law, path length we've covered with Lambert's law, but what is the molar absorption coefficient? Well, this is an intrinsic property of every solute and is determined by its chemical composition, so the number of single bonds, double bonds, ring structures, and both the number and type of atoms present. And all of these things together determines just how capable a solute is at absorbing light at a specific wavelength. And in basic terms, this means some compounds can absorb more light of a specific wavelength than other compounds due to its atomic configuration. And so a compound with a high molar absorption coefficient will absorb more light than a compound with a low molar absorption coefficient. But remember, this is for a specific wavelength of light. Some compounds are better at absorbing certain colours of light than others. Okay, so now that we've gone through the basics of the equation, let's take a second to see how this equation links into practical spectrophotometry. And so a spectrophotometer is the machine we use to measure the absorbance of light by a solution, and it does this by shining a specific wavelength of light through the solution, which is housed in a specialized plastic container known as a cuvette, and it will then measure the light that has passed through to the other side via a light detector on the other side. Now the way in which this all works is the spectrophotometer will shine light of a known intensity from the light source, which is known as I0, and recording the amount of light reaching the detector known as I1. Now it's the properties of the solution which change the light being detected, and so if we take our Beer-Lambert equation, we can see that the molar absorption coefficient of the solution along with the concentration will affect the absorbance of light, as will the path length. And if we take all of this information, we can put it into a single equation, meaning our absorption is equal to the log 10 of the light intensity entering the sample divided by the light intensity of the light leaving the sample, which is equal to epsilon multiplied by the concentration multiplied by the path length. Now, one of the most useful biochemical uses of spectrophotometry is the generation of what we call a standard curve via quantification. So this is where we will measure the absorbance of solutions with a known concentration of a particular solute. And a standard curve is where we graph absorbance against concentration. So here we have an absorbance at 600 nanometers on our y-axis plotted against the concentration of compound A in milligrams per milliliter on our x-axis. As you can see from the y-axis scale, we typically want to identify values between 0.1 and 1, and this is purely because outside of these values we can start to get some erroneous results. And so if we were to plot the absorbance of 6 solutions, each with a different concentration of compound A, we can see that as the concentration of compound A increases, so does the absorbance value, which can be shown with a trend line. Now we can use this known data and the plotted trend line to try and determine the concentration of solutions containing an unknown concentration of compound A, and there are 2 ways in which we can do this. The first is a very rudimental way, and we just measure the absorbance of our unknown solution and draw lines from our y-axis to the trend line and then down to our x-axis. Or you can do a more scientific approach and calculate the gradient of our trend line using the equation y equals mx plus c, which we can rearrange to give x equals y minus c divided by m. But why do we need to know all of that? Well, we can use Beer-Lambert's law and these standard curves to determine the concentration of solutions, and normally in practical biochemistry we measure absorbance to help determine the concentration by rearranging this equation using basic algebra. Now, to help make sense of all this, we're going to look at 2 different examples. And so in our first example, a student measures the absorbance value of an NaDH solution which has a molar absorption coefficient of 62,200 litres per mole per centimetre. Using a 1 centimetre cuvette, the student measured the absorbance value of the NaDH solution at 340 nanometers to be 0.512. After measuring the absorbance, the student wants to know what is the concentration of the NaDH solution. And so in order to do this, we need to bring up our equation and rearrange it to find C, giving us C is equal to A divided by epsilon times L. We then need to transfer all of our information from the example into our equation, giving us C equals 0.512 divided by 62,200 litres per mole per centimetre multiplied by 1 centimetre. Now, to make things easier, we can simplify this equation by completing the bottom line of the equation, giving us C equals 0.512 divided by 62,200 litres per mole, which we can complete to give us a concentration of 0.000000823 litres per mole, which is more commonly referred to as molar. Or, if we were to convert the number to something more manageable, we'd get 0.00823 millimolar. And we can convert this yet again, giving us 8.23 micromolar. Now, if this conversion between different units and varying orders of magnitude doesn't make sense, please check out the associated video on units of measurement. Now, moving on to our second example, some students are measuring the absorbance value of a 0.1 molar solution of compound X. They use specialized mini cuvettes that have a 0.2 centimeter light path, and the absorbance value at 600 nanometers was measured at 0.436. And so the students want to know what is the molar absorption coefficient for compound X. So in order to do this, we need to bring up our equation and rearrange it using some basic algebra to find epsilon, giving us epsilon is equal to A divided by C times L. We then need to transfer all of the information from the example into our equation. And this gives us epsilon is equal to 0.436 divided by 0.1 molar multiplied by 0.2 centimeters. Now, it's important to note that our concentration here is in molar, denoted by the capital M. However, this can also be expressed as the number of moles per litre, and so if we convert this to something more familiar, and something we have seen before, we can see that epsilon is equal to 0.436 divided by 0.1 litres per mole multiplied by 0.2 centimetres. Now, to make things simpler, we can simplify the bottom line of this equation, giving us epsilon is equal to 0.436 divided by 0.02 litres per mole per centimetre, which we can complete to give us a molar absorption coefficient of 21.8 litres per mole per centimetre. And with that, we come to the end of this basic laboratory calculations video. Hopefully you found the content useful, easy to understand, and can use it going forward in your practical sessions. Thanks for watching, stay safe, and I hope you have a great day.